In the last two lectures, we looked at some interesting dynamics in terms of inverse response systems, and then the difficulties that arise out of the inverse response and the difficulty in tuning controllers for inverse response systems and so on. So, before we go on to truly multivariable control, there are three different components of a transfer function which can lead to difficult dynamics as far as control is concerned, that we are going to look at. The first one was inverse response, and the second one that we are going to touch upon today and the next lecture would be time delay. So, in fact, time delay is a very important idea, and this is in some sense all pervasive. There is no system that does not have some sort of a delay in response, and all of us have felt this time delay in real life, and I will explain that to you as we go through this lecture. And it also turns out that controlling systems with time delay is a really difficult problem. So, in fact, this is one of the most difficult problems in control, and that is the reason why I kind of moved this all the way to this time in the course. I did not want to confound time delay ideas with other ideas which are reasonably clean and straightforward, and you could teach most of it using very simple ideas such as partial fractions, inversions and so on, which we have already seen. So, now that we have started escalating the complexity of the transfer functions and the kind of tools and techniques that we need to understand these types of systems, I think now is the time to look at time delay. And you will see that till now we were looking at transfer functions even if there were difficult dynamics such as inverse response. We were looking at transfer function of the form numerator over denominator, and we have been looking at transfer functions where both the numerator and denominator are polynomials. So, we did not have to go for anything very drastically different from basic stuff that we had learned at the initial portion of this course. Now, you will see that we will have a term which is going to be an exponential term, and that will kind of produce all kinds of complications in terms of both analyzing transfer functions, looking at stability of open loop systems, stability of closed loop systems and so on. So, basically first I will describe what a time delay system is, and from an open loop I will show that it does not really matter much because it is very simple inversion that happens when you have this exponential part. But when it comes to closed loop, you will see that there is going to be all kinds of difficulties because we are going to get this time delay term in the denominator, and that is going to completely change the way we do the inversion of these transfer functions that we have been looking at till now. And then of course, stability is going to be a totally new way of looking at stability. So, this is what we are going to see as we go through the next few lectures. So, before I describe the time delay in a transfer function, let us first understand how the functional form looks and how do you go from time to Laplace domain and so on when I have this time delay term. So, if I have something like this, y of s is, if I simply write this as, let us say e power minus tau ds u of s. So, if I write something like this, then this is the time delay term in the Laplace domain, and we call this tau d as the time delay. And if I have something like this and I want to do an inverse Laplace transform of this, Laplace inverse of y of s is Laplace inverse of e power minus tau ds u of s. So, if I have something like this, then if you go to the Laplace table and see this, you will see that this y of t will be u of t minus tau t. So, this is the Laplace inverse for this equation. So, whenever I multiply something by e power minus tau ds, then basically what you are saying is this output is going to be time shifted back by this tau d amount. So, this is the basic expression. So, what this basically says is, if you look at this equation, it says, let us say I make a change in u and I want to observe the change in y. So, I observe the change in y at time t for the changes made at time t minus tau d. So, whatever I made in terms of changes at time t minus tau d manifests itself only at time t. So, there is a delay of tau d time. So, I have to wait for tau d amount of time before I actually see the effect. Okay. So, this is the idea of time delay, and this is something that you see in real life. So, for example, if you have a long pipe, let us say, okay, at steady state the flow is constant, and then let us say it is a long pipe and suddenly you increase the flow here, let us say. Now, the effect of this increase in flow is not going to be felt here right away. So, all this intermediate liquid has to kind of go out before this high flow reflects here. So, if I think of this as u and this as y, right, if I see a sudden change here, let us say at 30 minutes, let us say in the flow, that is because something changed here a while back, right, quite a while back, and then that is the reason why I am seeing this change here. So, this is what is called the transport delay, and the amount of time it takes before something that I do here shows up here is what is time delay. So, if you want to think about it this way, if you say I make a change at u minus tau d and then I look at y t minus tau d, then I would not have seen, I made a change here, but that is not reflected here. Okay. So, let us say the next y also it will not reflect. So, it will reflect at y of t. So, this amount of time has to be lapsed or delayed before I see the effect of this here. So, this is a very important point, and this happens in all kinds of real situations and particularly flow systems and so on. Whenever you take an action, it takes some amount of time before you see the effect, and typically called as transport lag or transport delay. Now, similarly, just so that I show you this, because we are going to see this as we go along in this lecture. If y of s is on the other hand e power t ds u of s, then basically this equation says y of t. So, when I do the Laplace, this will be u of t plus tau d. So, the sign changes, right. So, this basically says that actually the input is going to lead the output. So, you might ask, why should I look at this? I can write this equation as u of s is e power tau ds y of s, right. So, that is the reason why we have to look at forms like this. But just so that you understand, whenever I multiply by e power some alpha s, then you basically say y of t is u of t plus alpha. If this alpha is negative, correspondingly it will be minus t. If it is positive, it will be plus tau d and so on. Okay. So, when we talk about, let us say transfer functions now, which we are considering. So, we again write here gm, which is used as a surrogate for g process. So, first order transfer function is something we had seen, which is k over tau s plus 1. Now, this basically means there is no delay. So, whenever I have a u that immediately acts on y is what this says, but in real life you will have time delays. So, when you have these time delays, the transfer function usually is modified by multiplying a e power minus tau ds. So, this is a first order plus time delay system. So, there are multiple interpretations for this. So, for example, if you say y s is basically k over tau s plus 1 u s, this is without time delay. So, this basically says y of t is going to be some convolution form between, let us say, some function g of t and u of t. So, some convolution form is going to be here. Now, a layman way to understand what impact this has is the following. So, if I say y of s is k e power minus tau ds by tau s plus 1 u of s, then this together I can add and then say this is y of s is some k over tau s plus 1, some delayed version of u is what I can write here, u d of s. So, this delayed version of u and u of s is related by, so this delayed version of u is basically u of t minus tau d, right, because I can write this delayed version as e power minus tau d as u of s, and from here I showed you this. So, basically what it says is, so in this case the convolution will be between some function and u delayed version, right. So, this basically says this first order is going to act instantaneously on changes to u. When I add a time delay system, it says the first order is going to act instantaneously not on u, but it is going to act on u t minus tau d. So, whatever changes I made a while back will affect the output in a first order form or passing through a first order transfer function. In the previous case, without time delay, whatever change I make currently will immediately affect y through a first order process. So, that is the idea of using here. Okay. So, that is an important thing to understand. So, any time this looks confusing, you can kind of club e power minus tau ds and the next term that you have, and then you will see what is the physical meaning, and that is what I tried to explain here. In the first case with just the first order, the physical meaning is that if there is no time delay, whatever u I have will immediately act on the output through a first order process. If there is a time delay, changes that I made at time t minus tau d will pass through a first order process and affect y. So, it will take that amount of time before you see any effect. Okay. Now, what is the problem with this, right? So, now if you want to quickly understand whether this creates any problems in terms of inversion and so on. So, you can see that it really does not create any problems in terms of inversion as long as this time delay term is in the numerator. This is because of the following. So, if I have, let us say, y of s is some g model times u of s, let us say this g model as a first order part and then e power minus tau ds, or I can write this as y of s is some numerator by denominator times e power minus tau ds in the numerator times us. Then whatever functional form we had used, the partial fraction expansion and so on, can be directly used here, because this portion I can actually put it in the partial fraction form, and then I can do the inversion, except that here this I will, instead of calling this as u of s, I will call it as u d of s, and in the convolution integral wherever I have u of t, I will replace it by u of t minus tau d, because u d of s is this here. Okay. So, in the convolution integral, finally when we do the inversion, we basically say it is simply a convolution with u of t, but I am just going to make it u of t minus tau d. So, in terms of doing the analysis open loop, there is nothing extra that I need to do. I can live with the same idea of partial fractions and then look at how I address this in the same framework, and it looks like there is nothing new or extra I need to understand or learn to handle this in the open loop. However, the minute we get into closed loop form, it is a totally different ball game, which we will see now. So, now let us try to design a controller using direct synthesis for this model form, which is k e power minus tau ds by tau s plus 1. And if let us say I were to decide that I am going to do this, and then I am going to do this, and I am going to ask for desired such as this tau s plus 1, then I want to see what happens here. Okay. So, to see that, I am going to show you a very simple computation. So, remember the controller is basically 1 over gm, g desired by g desired. So, in this case the gm is 1 over gm is going to be tau s plus 1 divided by k e power minus tau ds. Let us assume the g desired is something I have here, 1 over tau cs plus 1 divided by 1 minus 1 over tau cs plus 1. Now, after you do all the computations here, I am going to write the C of s here. The C of s that you will get is the following: tau cs plus 1 minus 1 divided by tau cs plus 1, tau cs plus 1, tau cs plus 1 will get cancelled. I will get tau s plus 1 divided by k tau cs, and then this e power minus tau ds will go up, e power tau ds this will become. Okay. Now, for people who have been following this course nicely, will immediately recognize that this is basically the PI form, right. So, tau s by k tau cs, s and s will get cancelled, that will give you the proportional part, and then 1 by k tau cs will give you the integral part. So, this they will see is as a PI controller. Nonetheless, there is a problem here, because we know the controller is a transfer function between the input and the error. Okay. So, u of s is c of s e of s, and remember I told you that when I write this u of s as tau s plus 1 by k tau cs e power tau ds, which is the controller e of s, right. Then basically what it says is, now this is a PI controller, and the PI controller is acting on a variable which is e power tau ds E of s. That means it is acting on a time variable which is error at t plus tau d, okay, and this is still u of t, right, because now this minus tau ds when it comes to the numerator has become plus tau ds. So basically what it says is the u of t, the current input that I need to compute, is a PI controller acting on error at time t plus tau d, okay. So now you see where the problem is, right. So to make a control move at the current time, I need to know what the error will be in the future, right, and the error is computed as the output minus the set point, and I do not have the output in the future, right, because I am at the current situation. So how can I get an error in the future to make a control move in the current situation? So that becomes an unrealizable controller. So if I just choose any G desired I want, then that is going to lead me to getting a controller that is not implementable, and that is not implementable because I need to have future errors for the current control move computation, and I do not know future outputs anyway, so I cannot do that. So this becomes unrealizable. So an interesting thing to notice is to think about this vis-a-vis the inverse response controller. In the inverse response model, because of this 1 over GM, we got an unstable controller, whereas when you have a time delay system, because of this 1 over GM, you are going to get an unrealizable controller, because the computation of the current input requires errors in the future. And much like how we did compromise in the case of inverse response processes, we are going to do a compromise when we do a control design for time delay systems. And before I get into the math of it, which is very simple, just like how we introduced inverse response behavior in the desired transfer function itself, which is the allowance that we are making, we are going to basically introduce a delay in the desired transfer function, which is allowance that we are making. So basically, just like how we described why inverse response systems are difficult to control, you can also understand why time delay systems are difficult to control. So I will give you two examples. One is something that all of us have felt at some time or other in our life, and the other one is I am going to go back to our own bike example and then tell you what kind of complications these time delay systems introduce. So all of us have taken a bath, we have taken a hot water bath. You typically go, you have a knob for hot water, you have a knob for cold water, and then you kind of open both the knobs and then say, okay, I will get tepid water to take a bath. But what you find is that you get extremely cold water to get a bath if the outside temperature is cold. This is because when you have these systems and you have pipes where water is there, because the external atmosphere is pretty cold, you have cold water in the pipes, and it takes a while for this water to drain out and the hot water to come from its source into the bathtub, right. So basically what it means is there is a transport delay. Though you have opened your hot water knob, this action is not going to immediately result in hot water coming, right. So all the water in the pipe has to drain out before the hot water comes, so that introduces a delay. But typically what happens is when you open the knob for the hot and cold, mind says, okay, hot water has to come in, but hot water is not coming in. So the first thought that comes is really not time delay, it is that maybe I have not opened the knob enough, so the flow of hot water is much lower than the cold water, so that is the reason why the water is still cold. So what you might do is you will increase the knob, then more flow is there, but still hot water is not coming in. But what happens ultimately is when if you open the knob too much, when the hot water comes in, it is going to be scalding hot, right. So this is something that many of us might have felt at some time or the other. So you see why this time delay create problems in control, because you have taken an action and you really do not know how long you have to wait, because you cannot get a very good estimate of time delay at all times, right. So you just have to wait, and you do not know whether it is really that you have not opened the knob enough, because of which the water has not become hot, or is it because of time delay you have opened the knob enough and you wait for long enough time, you will get hot water. So it is a very interesting question, and it makes the controller design that much more complicated, particularly if you do not have a very good idea of how long the delay is and so on. Now, it is interesting to kind of think about the same thing in the context of the bike example, and this will really tell you very nicely what the problem is. Supposing you are going on a road and you say, okay, there is a right coming up, I am going to take the right, and then you go on the road and then you move your steering wheel to the right, and the bike, if it has no time delay, the minute you move your steering to the right, the bike will turn right and everything will be nice. But if let us say you have this special bike which has a time delay, then you go and then you want to take a right, you move your steering to your right, but it is going to take some time before this action will reap its rewards. So, basically you keep going for some more distance and then suddenly the bike will turn right, but there will be no road to go because you have already missed the right. Okay. So, you can see how this time delay creates difficulties in control. So, the real solution is actually, if you know the exact amount of time delay, then what you really need to do is, that after I move the steering to the right, it takes about maybe 3 seconds for the bike to turn right. So, I am going at this speed. So, the intersection is going to come ahead. So, I have to estimate how long it will take me to get to the intersection. Let us say the minute I figure out that it is going to take me 3 seconds to get to the intersection, I have to move my steering and then stay with my steering in its new position, and exactly when you hit the intersection at 3 seconds, you will move right and be on your way. But look at how many difficult things you have to do. You have to understand your speed, you are going to figure out how long it is going to take you to get to your intersection, and that has to be precisely matched with time delay, assuming that you know the time delay accurately. If you do not know the time delay accurately, it might take 3 seconds, 4 seconds, 5 seconds, then you can see how complicated this computation even for the small example will become, and driving might not seem as much fun as it seems right now. Okay. So, you see the difficulty of control of time delay systems. So, much like the inverse response problem, for time delay also we are going to moderate our expectations in terms of the performance, and then we are going to say, let me not ask for any performance such as this 1 over tau s plus 1, much like how I introduced an RHP 0 to handle inverse response systems, I am going to equivalently introduce a time delay. So, this basically says that I know that there is going to be a time delay and I am going to live with it. So, I know that if I make a change in the steering to the right, it is going to take a certain amount of time before it going to turn right, and I am going to factor that into my desired behavior, so that I actually change the steering even before I get to the intersection. So, I have already constrained to include this. If I do not include this, then I am not going to get a realizable controller. Okay. So, once we do that, then I have a g desired e power minus tau ds tau cs plus 1, and just like how I explained in the inverse response behavior, by looking at this itself, we can say this desired itself is a time delay system, right. So, we are deliberately introducing a time delay in the desired to counteract the time delay of the process. So, again remember that this is basically a model of the process. The true process could have a time delay which is different from this, and the effect of what that will be we will see later, and it is the same process. You have to put the closed loop, the controller, once it is designed like this, the closed loop will have a process which might not have the same time delay, slightly different time delay, and then you can do the same analysis like what we did in the last class. So, that becomes now procedural, there is nothing new there, as long as you understand the distinction between a model for controller design and a process to be checked out in a closed loop diagram. Anyway, we know this formula, we have used this many times, g desired by gm times 1 minus g desired. So, I put this g desired, I have this gm k e power minus tau ds tau s plus 1, and I have this. Now, this and this will get cancelled, and this will get cancelled, and this will be tau cs plus 1 minus e power minus tau ds in the denominator, and this will go to the numerator, and then you will get your controller as tau s plus 1 divided by k times tau Cs plus 1 minus e power minus tau ds. So, this is the controller that we define for a time delay systems. Now, what we are going to do? We are going to look at this controller and then see whether we can realize this controller using techniques that we have learned till now, or are there other newer ideas that you need to address now controller of this form. You will notice that we have to bring in newer ideas to look at how to handle these types of transfer functions now, which are not your standard numerator over denominator transfer function form. So, what we will do is we will pick up from here in the next lecture and then talk about how you realize this controller and how do you think about looking at closed loop stability when you have time delay systems and so on. So, we will see you again next lecture to describe some of these. Thank you.